Thanks so much for being here, and hopefully you're enjoying all of these different modules that you're learning from. Today we're going to go kind of dig deep into something that sounds pretty specific. I personally think it's quite important. But what it is load factor. So let's go ahead and move on to the next slide and jump right in. So I give you here the definition of load factor, and people will, if you Google load factor, for example, what you might get is a plant load factor. In other words, like a capacity factor of an individual power plant. You can also have load factors for on the demand side for, say, a manufacturing facility or industrial facility, like how efficiently they're using their own power. In this context, I mean something that's bigger than that. And it is for a country, it's the relationship between the energy used in total over the course of a year to the peak energy demand in a given hour at that year. Really, it's given instantaneous. It's not really integrated over 60 minutes. It's actually instantaneous, but usually peak hours is represented in that, kind of time resolution in terms of when they measure it. So you take the energy as represented in megawatt hours, could be kilowatt hours, could be gigawatt hours, and divide it by the product of that peak amount times 8760. And what the load factor represents is the efficiency of the system with respect to mostly capital utilization, because you're always going to build your power plants to meet your peak demand. Otherwise, you will have a blackout like we discussed in the last module. So in order to do that, you might have, some plant that's sitting there and only running for 1 hour a year, or maybe 10 hours a year, but something that's quite small, and that plant is there to provide reserve. It's there to take up the slack if another plant has an unscheduled outage. But basically, it's a bit of a waste, right? To have a plant that's sitting there just lying sort of dormant, not doing anything for most hours of the year. In fact, for that matter, you can get into value of lost load and what it's worth to the economy to build that plant versus just going ahead and letting the power system go through, a deficit of power, a blackout basically for some hours of the year. And that's a whole other topic, but it's quite interesting to figure out when you look at your loss of load probability, how it makes sense to target that from an economic efficiency perspective. So this example here is taken from Northwest Power Pool in the USA. Northwest quadrant of the country, so it's pretty cold, right? I mean, Nevada can be quite hot with sun, but a lot of the population is living in that region in the states of Washington and Oregon, which is up in the Pacific Northwest. So why that matters is because air conditioning, again, is really the driver in most cases of your annual peak. Typically, that's going to happen in the summer. It's going to be really based on air conditioning load. So for Northwest Power Pool in 2018, they saw a 66.8% load factor for that regional system. So that's, good, bad, it doesn't matter. It's something that is really about relative to what they've been doing or where they're going. That's the important thing. And when I look at the forecast for NWPP, I see that they have increased their load factor and that they forecast it to go to, say almost 72% starting in 2021 and remain flat. So even in the US, where I think there's lots of very progressive regions who might be talking about demand response programs, time of use pricing, all sorts of ways to get customers incentivized to be more efficient about their energy usage. Even with that, they're still forecasting it flat. They're increasing it, so they're getting more efficient in how they're using their existing generation assets. But then they're like, well, we don't know. We don't know what it's going to do. We don't know if it's going to go up or down, so let's go ahead and forecast it flat. Next slide, please. So the influences on load factor, there are many, and I'm going to spend a little bit of time on this slide. I have another deck where I go into a slide per influence, right? You can go into deep detail on this. But when you think about what is going to impact the numerator or the denominator of that equation, you have counterbalancing influences. Rooftop solar, for example, will decrease the load factor because the numerator, which is that generation number, will go down in that this electricity demand is going to be met by a customer's own installation. So the generation number goes down, but the peak might stay the same. If that power is not being generated at that time of peak, or if what's influencing the peak is not based on sort of a standard daytime solar demand for power, then it will have a downward influence. You want this upward influence. You want, again, the system to be utilizing its capital more efficiently. If you have behind the meter storage, that can have an upward influence, because then you can shift your demand and your supply, both, right? It can have an influence on both sides of that equation. Smart technology will have an upward influence. And this is all based on the assumption that rates are structured such that there's a demand charge and an energy charge at the very least. And that rate structure could be quite a bit more disaggregated than that even. But demand charge means that you are going to get a charge based on what you are consuming in that peak hour. And if you can shift your contribution to the system's peak, or shift, help shift the peak itself to flatten it out, then that will again reduce your power bills and have an upward influence on the load factor. Industrial sector growth usually has an upward influence because that might increase that numerator, because industrial load is typically pretty flat. It might be base loaded. I mean, certainly it might not be perfectly flat, but it's not going to be influenced by that specific peak hour in the year. And so you're increasing the numerator. Electric vehicles, though, I mean, that could go either way, right? That could depend, but it will go down. It will decrease it. And that's because folks are going to drive to work in their electric vehicles. They're going to come home. They're going to plug the vehicle into their charging socket. So at that point, you've got that high evening peak where businesses still have the air conditioner running or the heating system running. They still have the lights on. And yet you're overlapping that with the domestic or residential sector's demand for power and increasing that demand through EVs plugging in. Energy efficiency will help load factor. Air conditioning usage will not help load factor. That will really influence the peak and push it up higher. Business hours will have, it depends on what the business hours are doing, but mostly that'll have a decreased impact on the load factor. And just, again, keep in mind that this is sort of decreasing it is bad. We want high load factor. So a decreased impact on load factor means that business hours are sort of overlapping, right? If you can shift the business hours to occur not during the peak hour, then that could actually change and have the upward influence. Captive generation means your own diesel genset, your own PV system, your own whatever it is, and that will have could have up or down influence depending on what the policies are related to captive generation. Demand response will always help reduce your peak, right? Time of use tariffs will always help. Electrification depends on what we're talking about with respect to what appliances and when they're used. And then blockchain technology will have an upward influence on the peak because pricing signals will be tied to energy uses in specific hours, and that will help the efficiency of the system. Next slide, please. So we're going to look at some country case studies, and you'll have this deck as a reference. I'm not going to spend time going into a deep dive on each country, but I want to kind of give you the basics of how there's two different ways to approach load factor. You can use regression or some other forecasting methodology to forecast your annual generation. You can also use that same set of variables or modify them depending to forecast your peak. And then when you do the calculation, the result is that load factor. So if they're diverging, if energy and peak are diverging based on their own natural forecast, then yeah, that load factor will increase or decrease slightly. But it's not going to go all over the map because they're so linked. The factors are so similar in, as far as what influences energy demanded and peak demand. However, most countries will do it where they're forecasting the generation based on, it could be an econometric approach. There's a lot of different approaches. It could be, through the machine learning type algorithm or artificial intelligence methodology that I mentioned previously. And then they take an assumed load factor and they apply it to annual generation, and then they derive their peak from that. So with that, that's what you're targeting in terms of your generation capacity expansion plan. You are targeting that result. So it really matters. What is the assumed load factor? Is it going to go up? Is it going to go down? Is it going to remain the same? In a lot of cases, it's going to remain the same because countries or utilities or planners just don't know what it's going to do. And so they just say, okay, well, we're just going to assume it's the same. Next slide, please. So when we look across countries, it's hard to compare. And one of the reasons is because that number for annual generation can be measuring different things. We might be looking at apples to oranges across countries. For annual generation, some might use gross, I'm going from top to bottom, like we're taking the biggest number and kind of pulling things out. So gross generation is what the power plants in aggregate actually produce. Net generation is what those power plants produce at the bus bar, what they push onto the grid because they have their own internal house power usage. But the system could be planning to net energy after imports and exports are accounted for. It could be just, if it's being done at the utilities accounting group and those numbers get pushed to the planning division, then that might be not including imports and exports. You could also pull off the losses, take off the transmission and the distribution losses, and look at the end user meter, what the annual energy consumed is, or you can pull off the non-technical losses, basically what might be lost to billing errors or theft or non-payment, and then basically the end sales number. And so when you look across different countries or different examples of, oh, what's their load factor? You just don't know. So you really need to look at how it's changing more than what the absolute number is. Next slide, please. Regardless, here is a set of numbers for some countries that we pooled together. We also provide that average seasonal temperature, hot or cold, depending. We include Denmark, for example, which is a winter peaking system. But you can see that load factor in India is quite high, whereas in Nepal it's quite low. And again, it's not really clear exactly what they're measuring, but that's the huge span that these numbers can have. Germany, extremely high. Turkey is looking really good too, if it's a true measure of the efficient use of capital. Next slide, please. So to give you an example of how the parameter that you choose for the numerator, the annual generation number, will have an impact on what the number is, I just show in Puerto Rico's case how utilizing either sales or net gen or gross gen can influence the level. So the generation and peak load are here on the left graph, left axis, and then when you calculate the load factor, you get this sort of, they're all the same relative to each other, but you have quite a different, 80% down to 65% depending on what number you grab. Next slide, please. So now we're going to dig into some case studies. For India, India, of course, is very progressive with respect to their clean energy targets, and they are very pro-policy, right? Very policy forward, which is lovely to see. So when they do their load forecasting, they have to consider all of the things that they've sort of put in place, and these include things like, I mean, everything from a reduction in transmission and distribution losses, which every system, I think, around the world is always forecasting that they're going to get better at that. So that's pretty normal. But they also have energy efficiency and demand side management programs. They even have a dedicated freight corridor, a rail corridor that's going to be fully electric to move goods around. And that investment and that plan is included in the consideration of what they're forecasting electricity demand to be. They do it state by state, so they do kind of build it up, and they try to go as bottom up as possible with this partial end use method. I know you're going to hear from other speakers to talk about bottom up versus top down. And it is hard for an enormous country like India to figure out how to pull all the pieces together, not double count, and not omit different energy uses. But they do consider it across categories. So they will look at different consumer classes and even down to, you know, what irrigation pumps are using and the capacity for the agricultural sector and that kind of thing. And again, expansion of the railways. They're looking at the initiative they have just to electrify everyone. And then they, of course, include the forecast for EVs and forecast for solar. Next slide, please. So here's their forecasted energy and their forecasted peak. And you can see the green line is that load factor. That is just the result, basically, of the dividing those two lines together. Next slide, please. Oh, that's the end of India. So yeah, so you can see that it's relatively flat. So that is how they just do it, you know, independently, and the result is that line. Now jumping to Afghanistan. Afghanistan's interesting because, this is a country of 34 provinces where only 11 of them are actually highly electrified, period. And I mean, most of them have no electricity or very little electricity. So when we talk about the power sector master plan, it's really only applying to a smaller portion of the country, like less than 1/3 of the provinces. So they do sort of a simplified econometric approach, and in order to do that, they've grabbed elasticity numbers from an economically similar country. And of course, donor banks, you know, help this country pull this together. But they, in particular, identify two factors that have an impact on forecasts. One is income development. So with respect to the residential sector, how much income is available for the residential sector to get more electrified, to buy more appliances, to, you know, have some disposable income to buy things that would demand power. With respect to the commercial and industrial sector and the public sector, that's really based on the relationship between those demands and GDP itself. Electricity price is a big factor in Afghanistan and the affordability of power. So how that price develops had in more than most countries had to play a role. So they spent a lot of time trying to nail down the price elasticity per sector. Next slide, please. And they are basically calculating that load from the load factor. Here are some of the parameters that they use for doing the general load factor forecasting. And you can see that Kabul and Herat they kind of span the usage, and when you exclude them, you can come up with the load factor forecast that is improving over time. So you can see from 55, 56, 58, 59, 60% over time. So they are accounting for a better use of the system through different behavioral changes. Next slide, please. So here you can see, you know, basically the peak demand and the annual generation, and then the computed load factor and how that improves over time. Next slide. Okay, moving on to Sri Lanka. We already talked about Sri Lanka in the other module. They do a very good job, very detailed job of doing the load forecast, and they consider developments in all industries, and they break out tourism, they break out transport, and like I mentioned in the other module, they consider special days because the profile of those days is significantly different than the standard weekday, weekend. And if you've ever been to Sri Lanka, you know that there's lots of sort of decorations, and during these holidays, they string electric lights to celebrate. And so there is a bigger draw at nighttime for that load. And similarly for, cricket matches and turning on the TV, you see a higher demand for power. Next slide, please. So here's the load factor for Sri Lanka. So you can see there is this assumed improvement in load factor from now-ish up to 2030, and then from there it stays relatively flat. I mean, again, that's just a fallout of the calculation. Next slide, please. So here they do the scenarios too, and I haven't gone into scenarios, but hopefully you've gotten it from some of the other trainers that it is key to do not just your base case, but to really look at high and low growth forecast and the factors that would influence them. They lend themselves to really looking at a spectrum of possibilities. And so for Sri Lanka, they have a reference case which is developed. They're having some help, of course, through, I believe that one was JICA, the Japanese investment bank. But at any rate, they've got different reference cases and then can kind of compare what they're coming up with through the bottom up versus the sort of top down straight econometric case. Next slide, please. So you can see that with respect to Sri Lanka, they have forecasted a modification of their daily curve. They're looking at different ways that will change, and there's an anticipation that in addition to a morning and evening peak, that daytime peak with the right policy could get higher and higher, competing really with the evening peak, which that flattening of the curve would have a great impact on load factor, assuming that they could keep that relationship on that one day of the year where it is the hottest, and then you're seeing your peak demand. Next slide, please. Bangladesh. Okay, and we're going to race through the last couple and try to stay on schedule here. So for Bangladesh, we have there was two methods that were used to forecast electricity demand in Bangladesh, and one of them was looking at basic sort of traditional econometric forecasting, and they do the peak demand specifically by looking at the GDP and the elasticity, so the dependency of that peak demand on GDP, as well as the bottom up that I talk about isn't customer by customer, but it's by sector, and they pool all the sectors together, forecasting them independently, and compare against the GDP method and sort of confirm that they're correlated. And when the consistency is confirmed, then they integrate both of those, and they have a hybrid approach that is, it saves quite a bit of time, and they can not worry about the data holes and still provide some of that resolution and that fidelity that you would get from more of a sectoral approach or bottom-up approach, and as best that they can get the data. So the trick with Bangladesh, though, is that there have been enough blackouts that, like I said in the other module, you don't know what you don't know as far as forecasting what the peak demand would have been had the system not blacked out. Next slide, please. So this shows the hybrid approach and pulling together the two different GDP elasticity method as well as that macro demand method, and sort of validating those two methods to provide that peak demand Next slide. Oh, I took out the slide that shows the how they figure out what the peak of Sri Lanka is going to be in the summer is they take the profile from a historic summer day, and then they look at the winter peak and they throw the curve on top of that winter peak in order to get that projected summer peak. But let's just move through Nepal really quick, and I can get you that slide in the final deck if that's helpful. For Nepal, we really want to show that depending on what of that annual generation number you choose, like I mentioned before, you kind of come up with very different load factors. And so, you know, just doing the math through all these things, you can see, okay, again, you've got the roll up of your generation, but of course it's going to depend on your exported energy as well as your losses and that kind of thing to get to what makes sense in terms of calculating that load factor. For Nepal, you can see that they have landed on 55% and then just grown it by 0.1% per year. So some slight improvement is forecast, but that's how they compute the peak load. Next slide. So you see here, it's, you know, you've got your blip in 2017 as that is like a historic number that came out of the actual demand, but overall they're forecasting relatively flat, but again, slightly improving load factor that's rolling out of their forecast for the energy demand, the total energy demand. Next slide. Good, we kind of caught up on time to try to get back on schedule. And I look forward to talking to you all during the open live question and answer session. Thank you so much for your attention.